All right. Good afternoon, everyone, and welcome to my talk. My name is Vivek Shah, and I'm from the University of Copenhagen, and this is joint work with Marcos Antonio Vasalis. So we are witnessing an unprecedented rise in the penetration of web and of mobile devices that is altering the landscape of online transaction processing applications. So newer online transaction processing applications span classical OLTP application domains like banking and reservation systems to newer emerging domains like massively multiplayer online role-playing games, bidding platforms, collaborative editing platforms, and online trading platforms, just to name a few. Now, in addition to the classic OLTP trends of being update heavy and requiring update consistency, these new OLTP applications also display some new emerging trends. For example, there is an increase in the amount of complexity in application logic, for example, decision-making logic, statistical computations, simulation logic that interacts with the data operations, data insert and update operations. Due to the user-facing nature and interactivity of these applications, latency is extremely critical. And because these applications need to scale to a large number of devices and to a large number of users, scalability is extremely important. So typically, these applications are deployed using a three-tier architecture where you have these client devices making some request to an application server where a program in a high-level language runs that makes a set of queries to a database server that sends responses and which is packed up and sent back to the client. Where the latency due to data shipping between the application server and database server becomes critical, then more of the application logic is shipped out into the database server in the form of stored procedures. Thankfully, hardware has been improving by leaps and bounds over the last decade, and modern OLTP databases have been re-engineered to leverage this hardware potential. But the programming interface of stored procedures has essentially remained. So the question is if this programming interface is good enough for this new world of OLTP applications and emerging hardware. So this programming interface of stored procedures faces certain performance challenges. Essentially, stored procedures are a sequence of queries. So there is no abstraction to reason about and leverage locality and intertransaction parallelism that might be available in the application logic when data partitioning is not enough. Due to lack of abstractions, it's also very hard for OLTP databases to provide low-level control over the deployment of these applications. On the software engineering challenge front, due to lack of modularity and isolation, as the size of the database in the form of the size of the schema, the number of stored procedures, and their complexity grows, it's very hard to maintain and debug them. And also, it's also very hard to reason about the performance of your stored procedures. So of late, we see that actor programming models have become increasingly popular for building middle-tier online services because of their modular, asynchronous, and concurrent programming primitive. And we observe that these set of primitives can actually address the challenges that are faced by the stored procedure programming model. So we think the time is ripe to think about integration of actor runtime features in relational databases, which forms the crux of our work, which is how can we integrate actor programming models in modern relational databases with high performance. So now that I have finished talking about the motivation of our work, I'm next going to talk about the design of the relational actor programming model before talking about the relational actor database system that provides this programming model before finally presenting some evaluation numbers. So the relational actor programming model or the reactor programming model consists of a set of concepts. Before I dive into the concepts, let me introduce a very simplified Bitcoin exchange application that I'll use to exemplify the concepts. So here we have a set of Bitcoin providers that provide some Bitcoin wallets to its users, and there's a Bitcoin exchange that performs swaps of Bitcoins to other currencies. So for this application, you can construct a schema where you have a relation to store the individual orders from the wallets and their settlement status, a relation to store the simulation of what is the risk associated with the provider, and a relation to store the thresholds for per provider exposure and risk. I'm going to elaborate on these concepts over the next couple of slides. So the primary construct in our programming model is that of a relational actor, or a reactor, which is an application-defined actor that encapsulates state abstracted as relation. So an actor is a logical, concurrent computational entity that provides you the illusion of a single thread of control. Now, from an application perspective, if you have to create reactors, you need to define a reactor type that consists of a schema and the methods that are available. And from this reactor type definition, you can create instances of reactors by providing them unique programmer allocated names that is used for addressing. So going back to our application, we can think of two reactor types, an exchange reactor type and a provider reactor type that encapsulates relations and has a set of methods. The code is not important. The basic takeaway here is essentially that you have types and they encapsulate relations and provide methods. And from these type definitions, you can create individual instances of reactors, each having their own unique names. So in order to access the isolated state within a reactor, you can use declarative queries. So that provides you with a rich space of reactor design. So if you create a reactor with all the relations and tuples encapsulated within it, then you get the classic relational model. While if you model individual reactors to consist of one tuple only, then you have the key value model. Well, you can also create hybrid models where you have different reactors consisting of different numbers of relations and tuples depending on your application need. In conjunction with the construct of an actor and by isolating the state within a reactor, this programming model provides modularity and isolation. So coming back, and we have our provider reactor, and in this we have a calc risk function that computes the exposure of a provider and ensures that it's within some threshold and then simulates the risk associated with this provider. In order to do that, you can use declarative queries to compute the exposure by summing all the unsettled orders. And then you can use this exposure to invoke a risk simulation and then return that as a result if need be. Now, again, the details of the program are not important. The main takeaway here is that you can use declarative queries to access the encapsulated state and mix that with some imperative code very similar to stored procedure programming. So in order to communicate with reactor instances, the messaging construct is of an asynchronous function call. In order to specify an asynchronous function call, you have to specify the name of the function, the parameters of that function, and the name of the reactor instance where that function is to be invoked. And the result here is a future that you can synchronize upon to wait for the function call to finish and to get the value of the result. Now, this construct of an asynchronous function call not only provides modularity and isolation, but it also allows you to leverage intertransaction parallelism and locality in your application logic, and it allows you to reason about the performance of your program in terms of the asynchronicity that has been leveraged in your code. So, for example, if I have my authPay method in my exchange reactor, which is supposed to authorize individual orders from these wallets, it needs to ensure that the total simulated risk across providers is not exceeded. In order to do that, it invokes the calc risk function on each of the provider reactors asynchronously so that they do the risk calculations in parallel. And then it synchronizes on the results to compute the total risk. And then if the total risk is not exceeded, then it invokes another function to add that order as accepted. Well, again, the details of the code are not important, but the basic takeaway again here is that you can leverage asynchronicity using asynchronous function calls and overlap them and then synchronize depending on the needs of your application. So there are certain automatic synchronization mechanisms in the reactor programming model to ease programming. So essentially, any method invocation on the same reactor is always executed synchronously to provide you the illusion of a single thread of control. Moreover, every parent method waits for all its children method that has been invoked by it to finish before it can finish itself. So here, if I have an execution tree where I have a set of asynchronous invocation of methods across certain reactors, method invocations on each level of the tree wait for the method, its children methods in the next level of the tree to complete before it can finish itself. Now, the reactor programming model also provides transactional guarantees. So the entire method execution tree happens within the context of a single transaction. So you get all or nothing atomicity, durability, and serializability guarantees. However, it is important to note that since reactors provide you with this illusion of a single thread of control, it is possible to have certain unsafe program traces. So if you have an execution trace that is cyclic across reactors, that is an unsafe program and is aborted. Similarly, if you have another execution trace where you have two outstanding calls to the same reactor instance that has not been ordered by the program, that is another unsafe execution trace and needs to be aborted. We also have a formalism of these programming model in the paper, which you can look at if you want. Okay, now that I have finished talking about the relational actor programming model, I'm going to talk about the design of an in-memory database engine prototype that we designed to support this programming model. So we targeted a single node multi-core machine with large main memory for deployment. So our architecture design problem is how do we map a set of reactors to the compute infrastructure of this machine? So one option is to delegate to operating system abstractions. So we could model each reactor either as a process or a thread, but that is not very desirable because it has overheads, and also it takes away a lot of the flexibility and control that you can exercise in a database system. So instead, we abstract a machine in terms of certain building blocks, and our first building block is that of a transaction executor that abstracts a single physical core. Our next abstraction is that of a container that abstracts a set of physical cores and the memory that is shared between them. So now what we need to do is first map transaction executors to containers, and then we need to map reactors to transaction executors under the constraint that a reactor can be mapped to only one container. This is important so that memory access asymmetries are not introduced within a single reactor, and because that breaks the illusion of locality that the programming model is providing you. So this mapping is specified at deployment time, and thus allows you to have low-level control over the deployment. Now, the architecture of our system visualizes a multi-core machine as a set of containers, where each container consists of a set of transaction executors and their request queue, and you have a transaction coordinator component that is responsible for commitment of transactions across containers, a transport driver component that is responsible for messaging across containers, and a transaction router component that is responsible for routing a specific method invocation to a specific transaction executor. So now, due to this architecture, it is possible to come up with multiple deployments of our system approximating different database architectures. So if you have a deployment where you have a number of containers, where each container just has one transaction executor, then you have the classic shared nothing deployment. And any transaction logic that is executed across these containers is executed in parallel. Now, if you have a deployment where you have a single container with all transaction executors mapped to it, and all reactors mapped to all transaction executors using a load balancing router, then you have the classic shared everything deployment. Another variant of shared everything deployment is possible where you have a single container with all the transaction executors, but a disjoint set of reactors are mapped to each transaction executor. And then you have a special router that tries to maintain memory access affinities. Now, in order to differentiate between these two deployments, we refer to the classical shared everything deployment as shared everything without affinity, and the other as shared everything with affinity. It's important to note that transaction logic that is executed within only one container is always executed sequentially. So hybrid deployments are also possible, but they have not been studied in the context of this work. So transaction executors consist of a thread pool that is pinned to a specific core, and they utilize cooperative multitasking to minimize context switches, and they use a configurable multi-programming level to maximize resource utilization. For concurrency control, we use the optimistic concurrency control protocol from Silo for single container transactions, and for multi-container transactions, we use optimistic concurrency control and two-phase commit. Now, relations of all reactors in our system are stored as primary key indices using adaptation of mastery from Silo. We do not have support for durability yet in our system. So now that I have talked about the system, let me show you with some brief evaluation numbers. So the first question that we asked ourselves was, can we leverage asynchronicity of the programming model using the system that we built? So for this, we use the workload of the simplified Bitcoin exchange application that consists of the auth-pay program that authorizes payment of orders from wallets in the exchange reactor. And we came up with 3 variants of this program to approximate different cases where you leverage different amounts of asynchronicity in your program. So we have a sequential version of the program deployed using shared everything with affinity container. Then you have 2 parallel variants of this program deployed using a shared nothing containers. So there is a query parallelism variant where you only parallelize the exposure calculation across the providers, but not the risk simulation. So that approximates the query parallelism of partition databases. And then you have a procedure parallelism variant where you parallelize both the exposure and the risk simulations. So we used a machine with 16 physical cores and 128 gigs of RAM for this experiment, and for a total and we deployed 16 reactors to map to the available parallelism of the machine. We used a single worker to generate our workload so we can focus on the asynchronicity gains. And in the workload, we are varying the complexity of risk calculation by generating more and more random numbers. So for this result, on the x-axis, I have the complexity of the risk simulation, which is approximated by the random numbers generation per provider in log scale. And on the y-axis, I have the average latency in milliseconds. And we can see that as we increase the amount of parallelizable application logic, different programs which leverage different amounts of asynchronicity, then different asynchronicity gains start to manifest. So the next question that we asked ourselves is, what about the effect of load on asynchronicity? So for this, we use the same machine as before, but now we used the TPCC benchmark, and where we modeled each warehouse as a reactor, and we use a mix of 100% new order transactions in the benchmark, all requesting items from a remote warehouse, and all the stock updates to remote warehouses are invoked asynchronously with a delay of 300 to 400 microseconds to simulate stock replenishment analytics. And we deployed 8 transaction executors at a scale factor of 8 in either shared nothing and shared everything with affinity containers. And we vary the load on the database by varying the number of workers. So for a result here on the x-axis, I have the load on the database, and on the y-axis, I have transaction throughput. And what we can see is that as I increase the load on the database, the asynchronicity gains diminish, which is offset by queuing. There are more experiments in the paper which you can look at. To conclude, with the advent of new OLTP applications and modern OLTP databases, we think the time is right to think about the stored procedure programming model. We designed the relational actor programming model, which marries the construct of an actor with the relational data and querying. And we built an in-memory database engine prototype called ReactDB to provide the reactor programming model that allows you to virtualize the database architecture at deployment time. If you're interested in talking more about our work, please come to our poster session tomorrow at 4. Thank you very much for listening. TPCC, right? Yeah.
So here, like, can you explain a bit more, like, what is the communication bottleneck?
Right. So what is happening here is, so here in the new order, I'm modeling each warehouse as a reactor. So in new order, I'm doing the stock updates across reactors, right? So what I'm doing, I'm invoking the stock updates per warehouse using asynchronous subtransactions. So when I have a single worker, I'm fixing the scale factor. So I have 8 transaction executors at a scale factor of 8. And then I have the entire resources of the machine available for me to process all the subtransactions. So that's why I see the maximum gains from asynchronicity. Now, as I add more and more workers, there are more, so I'm increasing concurrency in the system. So that puts a pressure on asynchronicity because of queuing, because they need to queue up in the request queues of the machine, and that diminishes the gain. So at some point, the sequential execution actually starts winning over the parallelized execution of the program.
So then, like, you need maybe more of a resource management, automatic resource management thing for the red line at least to, like, to reduce some pressure, not like more parallels.
Right. I mean, here so the entire deployment is specified manually for now in the system. So somebody would think what's the best deployment, and you would configure it. So as you increase more concurrency, the red line starts losing. So you might say that at some point I want to stop the red line and move to the blue line. So you might have some resource managers which change the deployment over time. That would be interesting. Yeah.
Start to
Right, so the question is like, where is the transaction implementation done? Okay, so what happens is we have this, so think the reactor construct is essentially a shim. So it's providing with all these concepts of the reactor programming model, but essentially when you compile it down and execute it, they're nothing but some lookups of data structures that map to certain transaction executors, and then within the machine, you have certain relations and index structures that are shared. And that's where the transaction implementation actually goes. So reactors are just an illusion to the programmer to leverage all this, and that is and in the system you implement all the mechanisms underneath where you kind of compile away all this shim.